Hello, welcome everyone. My name is Gretchen Specht. I'm the category manager with Thomas Scientific and responsible for chemistry. I just want to thank you all for taking time out of your very busy schedule to meet with us today. Today we're going to be discussing how to monitor your wastewater streams like a water pro. And I have the distinct pleasure of having Luke Johnson with us today. He is actually he's a chemist. He also has experience as a environmental engineer and a quality manager, and he is an expert in this field, and he's going to be sharing his knowledge with us today. He also, I also want to share with you that at the end we're going to be sharing some important application notes that list EPA compliant methods for wastewater analysis. Luke, I just want to thank you again for being here with us today and sharing your knowledge.
Thank you, Gretchen. And yeah, I'm really glad to be here. I'm really glad to have this opportunity, and I know Hawk is really thankful that we can partner with Thomas to present this webinar. So I also want to thank everybody who's jumped on. I know you're all busy, and this is like a really kind of weird time. Um, I'm at home. My son just started playing guitar and singing, and I can hear it in the background. So I hope that doesn't come through. Um, but I know I know it's really weird. It seems like everybody I've talked to is either like at home wishing they could get back to work, or at work wishing they had more time at home. Um, so thank you for taking the time, and in whatever situation you're in, I hope this presentation is beneficial to you and that you learn. Oh no, can you guys hear me? I just got a note that says, oh, okay. Okay. All right, great. Um, anyway, I hope you learn something and that you get something beneficial from this, to help you do more with less in a time when we may not have the same resources that we're used to having. Oh no, it sounds like a couple people also don't have audio.
Hmm.
What do you think, Gretchen? Should I keep going, or
I think
it?
so. Well, and Lauren's in the
Okay.
background. She'll figure out what's going on this. So Lauren can hear
Okay.
us. So yeah, we're getting some positive feedback. We'll figure out.
Okay.
Lauren is our backup here. So please continue.
Okay. All right, cool. Thank you. Well, let's jump into this presentation. Here's the agenda for this presentation. I want to kind of start out with just a review of who Hawk is, and then a discussion of water and how we want to take care of our most basic resource, um, and then the importance of waste stream monitoring, and then finally how to monitor your waste streams like a pro. And we'll finish it up with a special offer from Thomas Scientific. Also, I guess it goes without saying, but if, in case you didn't know, if you have any questions and you'd like me to address them, we will have a question and answer at the end, and you can enter that here in the chat screen. Okay, so at Hawk, it is our mission to ensure water quality for people around the world. This is um, really what gets us out of bed in the morning, and this is what Hawk is passionate about. I just grabbed a couple water facts here from one of our partners. Um, there are 4.4 billion people in the world that lack access to adequate sanitation. 2.1 billion people lack access to safe water, and one person dies every 37 seconds from a water-related illness. Um, Fortunately, in the United States, we don't see a lot of these same issues because we have some very stringent regulations, and because of the work that all of you water professionals do. But Hawk does operate worldwide, and ensuring water quality is really what motivates us, no matter the application. So, what makes Hawk different? Who is Hawk? At Hawk, we make water analysis better. So, from the very beginning, Hawk has striven to make water analysis faster, simpler, greener, more informative, so that you know that you're getting it right the first time, every time. So we've been doing this for over 80 years. Hawk Company was founded by Cliff and Kitty Hawk, and that was Clifford's vision as a chemist, was to make water analysis simple for everyone. So we try to incorporate simple, intuitive designs across all of our instruments, and all of our chemistries, all of our platforms. In addition to that, we have more EPA approved methods than any manufacturer. And we are currently we started in the US, but we are currently a global operation, manufacturing and engineering across the world. So let's get into water. Um, Water quality is an issue and a concern that spans every region and every industry. I'm just going to talk about the United States here. Um, in the United States, the we consume 322 billion gallons of water every day, which is a lot of water, and around 90% of that water is for industrial use. So these are just some images I grabbed from some of our industrial partners of water being used and running through their facility. Um, I listed a number of industries here that use water, and hopefully you can see your industry here in this list. If you don't, just mark it on your screen there at the bottom. I also stuck in an image here in the middle of this woman drinking some water because I want to highlight that that water quality is critical not only in industry where it's used, but eventually all of this water runs downstream into someone else's drinking water plant, at least in most cases. So, um, water quality is essential for industrial processing, but it's also critical to protect the environment and human health. Okay, this is a illustration of a idealized industrial plant, and what I want to demonstrate here is really where water touches many of our processes. So I don't know if you're at your plant or at home. Just imagine your facility here, whatever it is that you're doing. You may have all of these stops along the way, or maybe one or two, or other things that I haven't highlighted here. But go ahead and imagine your facility here. Down here at the bottom of the screen, we've got the raw water intake, and depending on what your water source is and what you're trying to do at your facility. Um, the water may be clean enough to operate with, or you may need to clean it up in some fashion. From that first interaction with water, um, it, let's let's take this path over here, and the water could go to a boiler and cooling system, which has other water quality needs. To operate an effective boiler and cooling system, we need the water to be a certain cleanliness. Maybe we're generating power there, and on the other end of that, the cooling tower, the cooling water is going to have other water quality characteristics that we need to account for. If we take this branch from the raw water over to the manufacturing process, um, there's a lot of water used in manufacturing. Maybe manufacturing in the product directly. For instance, if we're producing like beverages or something like that, or even if it's just something as a reaction medium, or for cleaning out vessels, water is used all throughout the manufacturing process at many facilities. Coming off of that, we have a QA QC branch here where water is used in the lab, but also a lot of analytical testing of the manufacturing process, of raw materials, of the final product. All of that, it requires great water analytics. And then on the tail end down here, um, at the outlet of all of these, we have a water treatment plant in many cases, and in all of them, a discharge to the environment, or discharge to a municipal water plant. Excuse me. So I just want to spend a second thinking about like what might be in this water. That coming into your plant, there's um, whatever's in your water, coming from your source, whether that's maybe a city water supply, so it's chlorinated, or it could be a river, so it has various minerals. And then as it passes through these various points in the industrial flow, what could be getting in there? Is there a product in this water? Are there treatment chemicals? Is there oil and grease, waste, analytical reagents coming from the labs? All of that stuff will join together into one stream as it's discharged. And frequently, this discharge is regulated with an NPDES permit. NPDES stands for the National Pollutant Discharge Elimination System. This is part of the Clean Water Act, and that's the program through which the state and the federal governments can regulate point source water discharges. So this is implemented as a permit, and a facility will have a specific permit that limits certain parameters to a certain level in a discharge, and there are operating costs associated with treating to get to those limits, and also fees and charges associated with exceeding those limits. So it's very critical to maintain compliance with your NPDES permit. So NPDES permits are kind of dynamic. I mean, they're written for a period of time, and then they are rewritten periodically to account for changes in manufacturing or changes in regulatory trends. So one of the things that we've been seeing frequently is that discharge permits are incorporating some new parameters, specifically nutrients. Um, nutrients, a high discharge of nutrients leads to eutrophication. That's what these images here at the bottom of the screen are. Eutrophication is a um, overgrowth of plant life. Here it's algae. And that overgrowth of plant life leads to deoxygenation of the environment or of the water, and then leads to animal death. So this is a dead fish. Um, this this is not happening at every facility, but this is generally what nutrient discharge limits are meant to prevent. So what are nutrients? The primary nutrient parameters are nitrogen and phosphorus, and those can show up in a number of different forms. For nitrogen, we got ammonia, nitrate, total Keldol nitrogen, and then total nitrogen. And for phosphorus, we have reactive and total phosphorus. And any permit could be written with any one of these parameters. Or oh, I think my headphones turned off. Can you still hear me? Okay, that's weird. Um, wow. Sorry, I apologize. So any of these can show up in any kind of permit, one way or the other. So for the rest of this presentation, I just want to focus on one of these parameters, just as representative for the rest. Just focus on ammonia here. It's a very common um, nutrient parameter. So let's look at what does ammonia testing look like. If this is your wastewater basin up here, this big brown body of water, and you want to test for ammonia, what are you going to do? This is representative of the typical historical ammonia procedure. Um, these are all, Hawk has been doing this for, like I said, 80 plus years. So this is all Hawk equipment, and this is an adaptation of the standard method, the Nestler method. And like I said, it's been part of Hawk's mission for decades to make water analysis better. So this procedure here on the right-hand side of the screen is representative of a vast improvement in ammonia methodology. So how does this test work? Basically, you're going to take your sample, add it to a graduated cylinder here. Then you're going to add this reagent, and then you're going to add this reagent, and then you're going to cap it and mix it. You're going to add some of this reagent, and then you're going to mix it and let it react for a while. And you're going to place it into one of these measuring cells, place the measuring cell into the spectrophotometer, and read the absorbance value of that sample in that measuring cell. So it's It's a multi-step process, requires several reagents and quite a bit of volume of sample, and also some pretty good analytical technique. I will point out that this reagent here, this tall bottle, is Nestler's reagent, which is 5 to 10% mercuric iodide. So contains mercury, which is obviously not a healthy reagent to be dealing with, either for humans or for the environment. But that is part of the traditional approved method. So I want to discuss some of the common analytical pain points associated with this kind of measurement. First off, the this can be complicated and time intensive. And if I don't know if you all have run this before, but there are quite a number of steps here highlighted that I'm just going to walk through briefly that makes this test take a lot more time than you would think it would take. Um, in addition to that, if I do the test one way and my other operator on a different shift does it a different way. There's a significant amount of operator to operator variability associated with this kind of analysis, and like I said, there are multiple analytical steps here where there's opportunities for errors, and just they're time intensive. So what do I mean? Let's just look at some of the steps here. There's reagent additions, and each one of these steps, there's an addition of a reagent to um, the sample. And I didn't mention this, but in this traditional method, you actually have to do this entire procedure twice, because you have to measure a blank and then you have to measure the sample. So double all of these things in your head. There's addition of a reagent here, addition of reagent here, another reagent addition here, and all of these are opportunities for adding the wrong reagent, adding the wrong volume of reagent, and anything like that will cause an error in the result. Then there are a number of mixing steps here. Mixing steps are missed, or if mixing is inadequate, there's also inaccuracy associated with that. Then there's also the reagent stability issue, because we have three different reagents. We have to keep track of all of these. Are these expired, or have they been stored properly? And each one of these needs to be monitored individually, because expired reagent will also cause inaccuracy. After that, we also have cell handling and alignment issues. Spectrophotometry is an optical method where we shine light through one of these cells here, and you'll notice on these cells, these both say 014 on them. These are optically matching cells, so that you can run the blank in one and the sample in another, and you know that the way that the light interacts with the glass will be the same for both of those, and you won't get a different absorbance value just as a function of the glass itself. Um, in addition to that, you could have a smudge on the window of this cell. You could have a scratch on the window of one or the other of these cells. They need to be turned in the same direction within the instrument every single time, so that you have consistent optical reading that way. And then finally, there's um, the pain point of the software interface. So this spectrophotometer, um, it's measuring the absorbance value of a sample, but in order to convert that into a concentration, we need to compare the absorbance to a known standard, and that's a calibration curve that's built into most spectrophotometers. Well, all the Hawk spectrophotometers, and this is an older model Hawk spec here. Um, but you have to choose the right method. You have to find it and load it, and there are multiple methods for multiple ranges, for multiple analytes, and it's not uncommon to kind of get lost in the menu structure trying to find exactly the right method for the application. So, in summary, on this slide, complicated methods lead to inefficiency, rework, and investigation, especially in a regulatory environment. And all of that is not helping you do more with less. Um, that's really a drag, and those are things that we want to avoid. So, other frequent common analytical pain points not associated with the methodology itself is regulatory compliance. Our wastewater methods are usually part of a permit, like I mentioned earlier, NPDES permit, and those are going to be used to determine compliance. And so those have to be approved by the local regulator, whether that's the state or the federal EPA. Um, the the regulator is always very specific about what kind of method can be used, and obviously they want a method that will work for the analyte in the specific matrix. So um, that's a frequent concern. Also, the method performance must be traceable. There needs to be very good data integrity around all the metadata of an analysis, like who is the operator, when did they run this sample, what was the condition of the reagents, which lot was used, and are they expired. All that needs to be accounted for in a comprehensive fashion, so that we can demonstrate that the measurement was taken in a compliant way. In addition to that, there's chemical usage and exposure risks and pain points. Many of these methods require hazardous chemicals. I mentioned earlier the Nestler reagent contains mercury. Common other reagents for COD or total killed all nitrogen contain things like mercury, chromium, cadmium, sulfuric acid, silver, lots of metals and acids that are um, not fun to deal with, not fun to deal with from a analyst standpoint, because we don't want to, obviously, like this image shows, we don't want to burn our skin or kill ourselves with the reagents that we're using, and we also don't want to damage the environment by using chemicals that will kill the life in the aquatic life downstream of our discharge. So we end up with this situation where the analytical reagents themselves can be hazardous to the environment and the analyst. So, end result, non-compliant analyses lead to financial and reputational damage. Um, and analytical reagents can create an environmental and safety hazard while you're in the process of trying to test for an environmental and safety hazard. So, um, a lot of things to think about, a lot of different issues that can go into what seems like a pretty simple measurement. And like I said, this is just ammonia that we're talking about. There are a number of other nutrients, and not just nutrients, but other analytes that are necessary to measure in water, in your wastewater in particular, and it could be a host of things depending on your permit situation. Um, so all of these things compounded in a representative lab, you might be doing any number of these analyses and dealing with all these pain points across multiple shifts um, and multiple operators every day. So Gretchen mentioned at the end of this presentation, we do have a list of um, uh, EPA compliant parameters that Hawk has for measuring in wastewater. So I encourage you to download that and check out your parameters. See exactly what kind of tests are available to ensure that you are measuring in a compliant fashion. So I walked through some pain points. Now we're going to get into what does it look like to measure like a pro. Um, and this is what Hawk has been building towards in the colorimetry realm. This is the DR39 spectrophotometer. Uh, this gray and blue instrument here, and these are the TNT plus reagent kits. Um, this is in summary, this is a fully automated visible spectrophotometer and self-contained vial reagents. I want to walk you through the way this works and explain why this actually helps alleviate a number of those pain points in the following slides. And then I actually have a little demonstration that I filmed that I think will be very illustrative. So this is just a diagram of how a spec works. Light shines through the sample, and in this diagram we have this little tiny cell here. This is 13 millimeters in diameter, which is what the size of these vials are, rather than the square cells that I showed on the previous slide, which are 1 inch, so quite a bit smaller. Um, let's look at at this in more depth. So this is a box of the TNT plus reagents, and I want to highlight a few things that make that illustrate the simplicity here. Um, uh, on the previous slide, I showed the method on the right hand side of the screen that had a bunch of different steps, and in this new reagent with this new reagent kit with these vials, we've narrowed it down to just 6 steps here, and they're all printed on the lid of the box. So um, and you can't really see all the steps here because there's some vial caps in the top, but there's no extra reagents to add. There's no glassware outside of this individual vial. It's all self-contained, and what that means is it's simpler because there's fewer steps, there's less equipment, and the operator training is super straightforward because there are just 6 steps with just this equipment. Um, in addition, all the reagents are pre-dosed, so no one needs to go in and individually add reagent 1 and reagent 2 and reagent 3 and do all the intermediate mixing and transfer steps. This also leads to greater accuracy and precision because the reagents are pre-dosed. They're machine filled, so there's always the exact same amount of reagent in every vial. We avoid accuracy issues associated with different volume transfers that you might see between different operators on different shifts. We also, if you look here at the vial, there are a couple barcodes on the label on each one of these vials. And as the vial is inserted into the instrument, the method is auto-loaded, and so there's no interface with the instrument that would lead to running maybe the incorrect method. Um, hey everybody, can you hear me now? Okay, sorry, this is so weird. Um, All right. I wonder. Well, I'm just going to jump in from here. If I missed something that you need to clarify, please give me a comment, and I'll address it. So this vial here is the shows the barcode, and if you imagine this being within the spectrophotometer, the light reads the barcode and loads the appropriate method. In this circumstance, this was a TNT 830 vial, which is the ultra low range ammonia. So it will load that method. It will load that calibration curve that was prepared by chemists at Hawk, um, and that was that was run through the EPA validation by chemists at Hawk. So it's all ready to go. What happens is the instrument will take the vial, it will turn it, it will read the barcode, and then it'll actually turn the vial 10 times and take 10 measurements as the vial is turned. And then it will take the average of those 10 measurements and throw out um, any outliers. So in this diagram, we have, this is looks like the 6th measurement here is 0.288, which is significantly higher than the others. And so the instrument will throw that result out because it knows that that is a statistical outlier that might be associated with a scratch on part of the vial or a fingerprint or something. Those were sources of imprecision in the previous method, but with the TNT plus vial and the way that it rotates through and averages out those values, that source of imprecision has been removed. Onto the other concerns, regulatory compliance. Like I said before, Hawk has more EPA-approved methods than any other supplier, and these nutrients, this ammonia procedure itself is EPA equivalent, and our other nutrient measurements are also EPA approved. This system also allows for data traceability. Every measurement is the barcode is read, the reagent expiry date is and lot information is read by the spectrophotometer and stored with the analytical measurement in the data folder along with the operator ID. So all of the metadata associated with the analysis are stored with every single measurement, and those can all be output, you know, to your LIMS system or your WIM system, or whatever kind of lab system you have. In addition, each box has this little RFID tag, and so every lot of reagents can be scanned at the instrument, and and all of the lot information is uploaded to the spectrophotometer, ensuring and guaranteeing regulatory traceability. I also mentioned environmental responsibility as a pain point. So we're always working to incorporate greener chemistries in the new um, TNT plus ammonia method. We don't use the Nestler reagent. We eliminated this mercury containing reagent altogether and use a different chemistry, which is obviously significantly greener. Um, I I know that every time I use mercury in the lab, it's like a huge deal. So if I can eliminate 50 milliliters of mercury containing reagent every single time I run this test, then that's a major plus for me, just from a EH&S standpoint. Um, we also have reduced the volume significantly. So this is a TNT plus vial here next to a larger, more traditional measuring cell, and you can see that there's quite a bit less volume. So even in those tests where there are still dangerous reagents incorporated, like this one is actually for a COD vial, um, the minimized volume also minimizes the risk and the environmental impact. We've also tried to improve operator safety by making these vials spill resistant. The lid or the mouth on this vial here is very tiny. It's in a rack, but the tiny mouth here actually prohibits, I shouldn't say it, it minimizes the possibility of spillage. It's designed specifically so that the surface tension of the liquid within the vial prevents it from spilling if it's knocked over. And I can testify that I have spilled these or almost spilled these near myself, and it actually did prevent more than just a drop coming out of it. And then finally, all the reagents are self-contained. So there's no opening up a bottle of reagent or opening up a bottle of powders and weighing those things out. They're all in either the vial itself here, pre-dosed into the vial as a liquid reagent, or lyophilized into the cap here if it's a powder reagent. And so there's the exposure risk to analysts is significantly reduced um, through this system. So what I want to do next is try and show you a video I made that's a side-by-side comparison. It's only a couple minutes long, and I'm just going to um, walk you through what's happening here. Can you guys see my video? Okay, cool. So this is my lab. This is the TNT plus reagents over here, and this is the traditional ammonia reagents over here, and this is the DR 3900 spectrophotometer, which we can use to measure, either way. So I'm just gonna talk over this. All right. So on the right hand side, I'm getting my graduated cylinders ready, and I'm going to add blank to one of these guys and sample to another. And I've got to add exactly um, 25 milliliters here. I, that was a really good pour job on my part, I gotta say. Um, Doing it with a bottle here. On the left-hand side, we got a TNT Plus vial, and we're just adding sample directly to the vial. And that is it as far as reagents. On the right-hand side, we're adding the first reagent. Wiping off the vial here just to get it clean. Adding the second reagent, and I'm already finished on the left-hand side. Now I'm going to mix these guys up. now I'm going to add the Nestler reagent. So I'm creating 50 mils of mercury containing waste for every sample. Mix this guy up. You can see the color change there for the sample that actually has ammonia in it, and that's what we're going to measure in the spec. So I'm going to transfer these to the two matching cells. And clean these guys off. Make sure I have no fingerprints on there. And then we're going to go and measure in the spec. So again, we got the have the TNT plus on the left-hand side, where I just stick it in the instrument, and you can see it starting to read the barcode. Now it's spinning, making its measurements. Boom, it's done. On the right-hand side, I found the method I needed. I loaded it. I just ran the blank. Now I'm running the sample, and boom, it's done. Um, you can't see it off of that screen, but all of the lot data is also stored with the TNT Plus for that measurement. So here's, like I alluded to earlier, all of the reagents and all of the glassware needing to be cleaned up. Um, it's quite a bit quicker, quite a bit safer, quite a bit well, quite a bit better. I'll just end it with that. So I wanted to share a little story about a customer that I was able to help recently. This is a pharmaceutical plant here in lovely Colorado. Um, the wastewater and facilities manager contacted me because they needed an EPA approved way to measure nutrients for both for process monitoring and for reporting, because they had a permit change. So um, they hadn't previously been looking at these things, and they started Googling around, like, how do I measure total Kaldol nitrogen? How do I measure ammonia? And his facility, his staff, they're not chemists, so they weren't comfortable with a lot of the instruments and techniques that were generally used in analytical labs, and he was very hesitant to proceed. They were looking at sending all their samples off site to be tested. So I was able to show them the Hawk TNT Plus system. Um, and I actually was able to go down and train their operators. They had one operator, and she worked on night shift, who was trained to run their EPA methods. And so I was able to train the whole staff on all the shifts in about a couple hours on multiple different nutrient parameters, and now they're all able to run these methods throughout the day. We also eliminated the Nestler reagent that they had been using historically and replaced it with the new TNT Plus ammonia chemistry. So they eliminated mercury waste stream from their lab, and in short, in the end, they built this into their permit, and now these procedures are part of their compliance testing going forward, demonstrating their compliance to the city. They discharge to the city. So I wanted to sum all this up and bring Gretchen back in. We're doing an offer with Thomas Scientific on the DR3900 spectrophotometer through July 17th. We're offering a 10% discount on the 3900, and I will go to this link. But if you're interested, go ahead and copy this down. This is um, thomassci.com/hawk-webinar. So if you would like to see more about this and download the application note that Gretchen mentioned earlier, go ahead and go to this website. And with that, I would like to turn it over for questions.
Thank you, Luke. That was awesome. If anybody has any questions, please feel free to type it into the chat box, and Luke is here, our expert, to answer those. In the interim, I just want to thank you, Luke. That was fantastic. Because water is, critically important and a finite resource. Um, what you shared today is invaluable. Thank you for that. And I also want to to share with the team that we do have this EPA compliant methods available for wastewater, and we're going to be emailing that out to you as well, just to make it convenient. And then the promotion, as you see up on the screen, is for the DR 3900, which, as you see, is a very easy to use. It's actually well recognized as highly accurate. And if anyone has any interest in that, please feel free to reach out to your Thomas associate, and they'll be able to assist you with that. So, um, if there's any questions, please feel free. Now is your chance to either ask the expert. I doubt you can stump him.
And I would be glad to answer questions offline too if anybody has any of those afterward.
Yep. All right. I think you were very thorough in your explanation today, Luke. So I think that everyone has their questions answered already. So actually, we have a Jill Jordan is asking, can you please comment on how to dispose of the vials?
Yes, that's a great question. So that is going to be dependent on the vial. So um, for well, we have a couple systems for that, and for the reagents that are not chemically hazardous, toxic, that don't contain, um, for instance, mercury or chrome, those vials can be disposed of. Um, through your site's regular disposal system. I don't know. However, your lab or your facility handles those. Those can be disposed in that fashion. Hawk actually offers a recycling program for the COD vials. Um, those do still contain mercury, chrome, silver, sulfuric acid. They're actually pretty nasty, but that test is I mean, that's the test. There's no getting around. It's a method defined parameter, so there's no getting around those specific reaction conditions. And so those, what we've minimized the volume, but we do actually offer a recycling program for those vials that we can send you a bucket and you can fill up the bucket and send it back, and we recycle those.
Excellent.
Mhm.
Alexan asks, how does using the DR 3900, how does that compare price wise to the traditional method of doing this analysis?
Yeah. So another great question. I actually have a kind of a calculator that I wasn't able to share just given the time frame of this, but maybe I can share it with you guys later. The reagents themselves, the TNT Plus kits, are more expensive than the traditional reagent bottles. That being said, um, we have we have a calculator that can show you just based off of the number of samples that you run, and the fact that you have to run blanks, and the costs associated with disposal, that there is a payoff period, 2 or 3 years down the line, depending on how many samples you run. I shouldn't even say 2 or 3. It's totally dependent on how frequently you run samples. So your return, could be much quicker or much longer. Um, that that over time it will actually save you money to not have to dispose of all of these chemical reagents, and not to use as many reagents because you don't have to run a blank every time you run a sample.
So that sounds pretty straightforward, right? I mean, obviously, the more you use
Yeah,
something, the least, the lower the cost is, and
for
then
sure.
savings on the reagents, savings, on basic time. So there's a lot of advantages.
Yes,
Uh, Kelly Walker asks, how do we sign up for the recycling program?
that is that's a great question. That's something we can do directly through Hawk, and I guess Gretchen, we need to talk about doing that through Thomas because
I
it's
think
not
that's a
something.
great idea.
Yeah. So, Kelly, I think we're gonna have to get back to you on running that through Thomas.
Super. Any other questions? Well, fantastic. It's been extremely informative. I learned a lot today, so I just want to thank you for that. And I'm confident everybody on this chat, on this program, also learned a lot. So I look forward to doing this again in the future. Thank you for
Great.
taking the time, both Luke and everyone on this video conference. It's been wonderful. And again, if you have any questions regarding Hawk products, the DR 3900 in particular, please feel free to reach out to your Thomas associate. They'll be happy to help you. Take care and enjoy life.
Thank you very much. Have a great day.
Bye bye.